All right, let's go.
I'm just gonna do that. It's a meeting.
So I think there was one problem for us to finish on this, so let's actually get through that before moving on. The big one. So again, it's handling systems. Problem 3. So what I did was, especially for my last class, there's a lot of text here. Want to make sure that we're not misreading anything. So what I would probably do is put this data in something else so I don't lose track of it. So that's what I'm going to do first. A, B, C, D. So we have some mixtures here of plant food. Mixture A, Mixture B, C, Mixture D. So this is the mix for plant food type. There's some phosphoric acid. We also want to worry about the nitrogen content. We also want to worry about the potash. I think it's some sort of potassium compound. And we're going to call the number of barrels here x1. That's the number of barrels. x2, x3, x4. All right, so let's get through this problem here. Farmer can buy 4 types of plant food. Each barrel of mix A contains 20 pounds of phosphoric acid, 50 pounds of nitrogen, and 20 pounds of potash. For mix B, there's 20 pounds of phosphoric acid, 75 pounds of nitrogen, and 30 pounds of potash. Mix C, 20 pounds of phosphoric acid, 25 pounds of nitrogen, and 30 pounds of nitrogen. And mix D contains 40 pounds of phosphoric acid, 25 pounds of nitrogen, and 50 pounds of potash. Okay. So that's different plant food mixes that you could buy and how much nutrients they have of each specific kind of nutrient here. And soil tests indicate that a particular field needs 540 pounds of phosphoric acid. So 540, here's the total needed. Uh, 650 pounds of nitrogen, and 720 pounds of potash. How many barrels of each type of food should the farmer mix together to get this kind of nutrient composition? That's the question. And the number of barrels of A that he has to mix, the number of barrels of B, C, and D that he has to mix, we call these X1, X2, X3, X4 in total. So basically I'm going to set up an equation for each one of these guys. So for the phosphoric acid, I know I get 20 pounds per barrel for mix A, plus 20 pounds per barrel for mix B, plus 20 pounds per barrel for mix C, plus 40 pounds per barrel for mix D, and I want that all to add up to 540. For the nitrogen, well, I need 50 pounds per barrel here, 75 pounds per barrel here, 25 pounds per barrel here, 25 pounds per barrel here, and I want that to add up to 650. And for the potash, 20 pounds per barrel, 30 pounds per barrel, 30 pounds per barrel, 50 pounds per barrel. I need 720 of that. So turns out to be able to answer this question, how many barrels do I need of each kind, it ends up being, we have to solve this system of equations. A couple things right off the bat that we can tell. We have 4 unknowns and only 3 equations, which means we definitely won't be able to solve for everybody, which means there's either going to be no solution or infinitely many solutions. What does infinitely many solutions even mean in this context? We'll see. So, what we're going to do is to solve the system. Let's create an augmented matrix, because that's how we do it. Before putting it in, I'm probably going to reduce, I believe, does 20 go into everybody here? Does 20 go into 54? Yeah, how many times? 27. So this is 1, 1, 1, 2, and 27. So what I did, I just took row 1, divided through by 20, and I would have 1, 1, 1, 2, and 27. Equal sign's going to be here. I think 25 goes into everyone here, right? At least. 25 into that goes 2 times, 25 into that goes 3 times, 25 into that goes 1 time, 25 into that goes 1 time. 25 into 650? 26. What goes in everyone here? Maybe 10? 10 into this 2, 10 into that 3, 10 into that 3, 10 into that 5, 10 into that 7, 2. So I can solve this problem by solving this system of equations here. Of course, we're going to want to get this to some sort of echelon form. So pivot is here. He's actually okay, so I'd actually not do anything with the first row. But I do want 0 here and 0 here right away. And so what can I do? I can do something like row 2 minus row 1 minus 2 row 1. Let's see there. So this minus 2 times that, 0. This minus 2 times that, 1. This minus 2 times that, minus 1. This minus 2 times that, minus 3. This minus 2 times that is going to be what? So you can take 26 minus 27, you get a negative 1, minus 27 again, you get a minus 28. And I want a 0 here. What I can do is say take row 3 and subtract row 2. This minus that, 0. This minus that, also 0. This minus that, 2. This minus that, 4. This minus that. 46. So we have that. In fact, I can probably even divide this by 2. So this is 1. This is 2. This has 23. So we have all our pivots with zeros below them whenever possible. Let's get our zeros above. Let's make a 0 here. We can do that by row 1 minus row 2. 1 minus 0, 1. This minus that, 0. This minus that, 2. This minus that, 5. So row 1 minus row 2. 27 plus 28 is what? 55. 55. What I would like is this to be a 0. I can get that by adding row 2 plus row 3. This plus that, 0. This plus that, 1. This plus that, 0. This plus that, minus 1. This plus that, minus 5. And this is pretty much okay at this point. One more thing, let's kill this 2 here. And I can do that by taking row 1 minus 2 row 3. This minus 2 times that, 1. This minus 2 times that, 0. This minus 2 times that, 0. This minus 2 times that is going to be 1. This minus 2 times 23, 2 times 23 is 46. Right? So if I take 55 minus 46, 9. 0 minus 1 minus 5, 0, 0, 1, 2, 23. You guys ever saw that YouTube video? It's awesome. Where it's from this old movie about Hitler and he's there, 999. And what everyone does is that they put subtitles that, because no one knows what they're saying in German, so they put subtitles about all sorts of things. There's this awesome one about math where he couldn't understand set theory. It's like, well, the set is both open and closed. 999! It can't be. It's awesome. You should see it. Okay. Yeah, so this here is reduced row echelon form. Any row of zeros is at the bottom, we don't have them. First non-zero number in every row is a 1. The ones have zeros below them and above them whenever possible. So now what I can do is notice that this is our x1 column. So x1 has a pivot in this column. This is our x2 column, has a pivot in this column. This is our x3 column, has a pivot in this column. The x4, well, he doesn't have any pivots in this column. So the x4, that's one. That's the guy that's going to be the free variable. It's not inconsistent, so this has a solution. In fact, this has infinitely many, depending on what x4 is. So because x4 has no pivot in the column, set it to be a free variable. So the x4 can be whatever it wants. We can solve for all the others. So, because I can't bother writing out x4 all the time, let's say it be like t or something like that. And then you kind of go from each row, starting from the bottom one. So according to row 3, you would have x3 equals 23 minus 2t. And from row 2, we would have x2 equals t minus 5. From our row 1, we would have x1 equals 9 minus t. So that's our solution to the system, and we have one solution for every t value. Or do we? Does it make sense for any t value in this context?
The only one where you make it negative, right?
You can be negative. What else?
0.
You could be 0. You could tell the farmer, don't buy any of these. That's possible. What else? Within context, what kind of solutions would make sense here? Whole numbers. They have to be whole numbers. They have to be non-negative. Those are the only ones that actually make sense. You can't buy pi barrels of something. You have to either buy 0 or 1 or 2 or 3. So while technically this is an infinite number of solutions, there are not an infinite number of applicable solutions. Notice that the viable solutions must be non-negative whole numbers in this case. So technically here, not an infinite number of solutions would work. Let's actually figure out which solutions would work. So to make sure that we have non-negative whole numbers, what's our restrictions here? What does t have to be? Well, just greater than or equal to 0. What about this one? What's your restriction on t here?
13. It's got to be less than 13, right? 12.
It's got to be less than 12. So here, t can go up to 11. Right, so it's definitely bigger than 0, but it can't pass 11 according to this one. Because at 11, you subtract 22, you buy 1 barrel of this. At 12, you have a negative 1 barrel. That's not going to make any sense. So we need that, we actually need this to be greater than or equal to 0. You can actually solve for t here. You'll get 12 and a half. You can't buy a half a barrel, so 11 is going to be the maximum here. Here, what do we need?
Greater than 5.
It has to be bigger than or equal to 5, right? So here we know that the t must be larger than 5. Here, less than or equal to 9. Right? Once it's larger than 9, now you're getting a negative number. So now, this means putting these together. We have solutions for, well, your t has to be, it can be as low as 5, 6, 7, 8, or 9. So there's actually only 5 applicable solutions here. All right, so there's 5 possible situations that could fulfill the farmer's needs. Let's actually write them down. I.e., A, B, C, D, or the number of A, number of B, number of C, number of D, has to be, well, it could be 1, or 2, or 3, or 4, or 5, and 3. Okay, so let's actually fill this in. Our t has to be between 5 and 9, so it can be 5, 6, 7, 8, or 9, which means x4 is actually the t, x4 is in the last column here. So we can have 5 barrels here, or 6, or 7, or 8, or 9. That will give us possible solutions. Now, in the event that t is 5, the x3 is going to be, well, 23 minus 10, right? So that's going to be 13. Now, every time t increases by 1, 2t will of course increase by 2. So this is actually going to decrease by 2 going all the way down. Then here, if t equals 5, that guy equals 0. But as t moves down by 1 each time, this will increase by 1. Up by 1 each time, this will increase by 1. So that's 1, 2, 3, 4. So when t is 6, that's 1, t is 7, that's 2, and t is 8, that's 3, and so on and so forth. And then for x1, when t is 5, that guy is going to start at 4. And then when it goes to 6, it's going to be 3, then 2, then 1, then 0. And these are all the possible solutions. So there are 5 scenarios that could actually work here. And yeah. So even though theoretically we have infinite solutions, sometimes based on context you have restrictions. And here you can note, so this will be the solution here. Pretty much all of these. The farmer has 5 options. Solutions can be further refined given other restrictions. So such as cost, availability, that sort of thing. Etc. Right? So if a guy comes to you and says, this is the situation, here's what my field needs, here are the mixtures of all the plant foods I can buy, what should I buy given that these are my needs? Well, you have 5 options. And then maybe he doesn't like the guy at the salesperson for plant food B, so he's like, yeah, I'm going to pick that option. Or maybe, you know, certain things are more expensive. Maybe plant food C is very expensive, so he's going to choose the solution that has the least amount of that, right? But now you have a refined set of options to actually choose, and you can actually narrow it down with more information. So here we have 5 possible solutions to this problem. Questions? In the remaining time, let's see how far we can get with the next topic. I was hoping to finish these last time so we can just start with a brand new topic, but such is life. So the next thing is going to be, I don't know, I like it, it's pretty interesting. I don't know if the reason I like it is because even I myself haven't done it enough. So systems of equations, I've seen systems of equations so many times, okay, fine, whatever. Row reduction, another row reduction. But I don't deal with linear inequalities very often, so it's still kind of fun for me to teach them. So we're going to talk about linear inequalities, and ultimately, this is going to lead us into linear programming, as it's called. And when we get to that, I'll define for you what linear programming is. But it has many applications, particularly in business settings, believe it or not, and certain social science settings. You go far enough in science, in the sciences, you're probably not going to have much use for linear programming, though you might. But with business applications, we use these guys all the time. So linear inequalities, let's actually talk about what those guys are. Gonna have to define some terms for you first. Okay, here, what is a linear inequality? Let's start with that. One thing I want you to also realize that we're only going to be using 2 variables. Because we're also going to be sketching them and using the pictures to do stuff. And once we go to 3 variables, now we have to sketch things in 3D. It's not going to be fun, at least not at this point. So we're focusing on 2 variables. A linear inequality in 2 variables. Is an inequality that can be written in one of the forms. You'll either see it look something like ax plus by is less than c, or you'd see ax plus by is less than or equal to c, or you see ax plus by is greater than c, or ax plus by is greater than or equal to c. And here, x, y are variables. They're the guys you're going to want to be able to solve for. And a, b, c, d are constants with a certain restriction. A and b, they cannot both be 0 at the same time. Any object that looks like that is called a linear inequality. And it's, the ones in 2 variables means you have 2 variables, that's it. So it's pretty much a lot like an equation, except the equal sign is replaced with an inequality sign. Less than or equal to, greater than or greater than or equal to. Now, the solution to these, they aren't going to be isolated numbers. They're actually going to be regions in space that will satisfy the inequality. Now, the solution to a linear inequality will be a region in two-space called a half plane. Why is it called a half plane? Because if you were to sketch one of these guys, you'll sketch it looking like a line, and the region of space that will be the solution will be an entire half, one side of that line. So your solution is an entire region of space. It will have, in general, an infinite number of points that will solve this inequality. Let's actually talk about graphing them and figuring out where the solutions are. So here are the steps. 1. First, sketch the line ax plus by equals c. So first, let's draw the line as if it were a regular line. Remember, you only need 2 points here. Don't waste time with more than that. You only need 2 points. Whenever possible, and usually for us it will be, the x and y intercepts will usually be the most convenient points. Okay. And basically what you can do, pretend x is 0, solve for your y, plot that on the y. Pretend your y is 0, solve for the x, plot that on the x-axis. Once you have these 2 points plotted, draw a straight line through them, and that's your graph. So that's going to be the first part. And 2, you must determine the half plane whose points satisfy the inequality. Probably should have said something before that. I'll say after. 2a. There are 2 ways to do this. One option. Pick a random point in a half. And check if the inequality is true for this point. If yes, shade the half plane. If no, shade the other half plane. That's one option. You can actually plug in a test point. We're going to do an example where we're doing this. I just want you to know what we're looking for, how we can actually do it. To be or not to be, another option is to basically solve for x or y and conclude based on the following. So if you solve for x, or let's do solve for y first. Let's say you solve for y and you see that y is greater than the ax plus c, or y is greater than or equal to the ax plus c, then what you do here is you would shade above the line. And if you have y less than ax plus c, or less than or equal to ax plus c, you shade below the line. If you chose to solve for x, which for some reason you might want to do that, then the possibilities are you can have x greater than or equal to the other side, or you can have x less than or equal to the other side. And in the event that your x is larger than this expression, you will shade to the right. And in the event that your x is smaller, you shade to the left. So you have a couple options here. You can plug in numbers into your equations, see if they actually make the inequality true. And if yes, you shade that region. If not, you don't shade the other region. Or if you solve for x or y, you can decide to just shade based on what position the region is in. 3, which I probably should have said before too, but there's no fun, I guess. It's just a convention that we use here. For greater than or less than, use a broken line. So have something like when you're drawing the line, you draw it as a broken line. And for greater than or equal to, or less than or equal to, use a solid line. So how you draw the line will depend on what kind of inequality you're talking about. Strictly less than something, meaning the boundary is not included, you draw it as a broken line. If the boundary is included because it can actually be equal to the line, you draw a solid line. And basically, when we're talking about solution, the graphical solution at least, it's going to be the shaded region. The solution is the set of all points in the shaded region. Whew, that's a lot of writing down, but needs to get some definitions straight. Let's actually do some examples, some simple ones. Let's start with some simple ones. Example. Sketch the solution to the following. A, y is greater than 1, B, x is less than 5, C. 2x minus 3y greater than 6, dx plus y is less than 2, x minus y is greater than 4. I'm going to sketch the answers for this. I'll wait for you guys to finish copying before I jump into it. Yeah, I don't think we're going to make it past this, but next time we're going to look at systems of linear inequalities, and that's going to be okay. For now, let's deal with one inequality at a time. Eventually, we're going to want to be able to solve multiple of them at the same time. So A, y greater than 1. What do you do? Use a broken line to sketch y equals 1. So you pretend it's an equation and you sketch that equation. What does y equals 1 look like? Horizontal line going across here, but you draw a broken line. Right? Going through 1. Now, this falls really nicely with the second method of figuring out what the solution is. I have y's bigger than something, which means the y is on top, which means this entire region here. So there are a couple ways we can know that that was the solution. So 1, because we have y greater than blah, shade above. The second way you could have figured this out is to pick a random point that you know is in here and actually see if it's true. So I could pick a point, for example, that I know for sure is on one side of this line. Let's say I picked 0, 2. This means that your x is 0, your y is 2. And so if I picked 0, 2, this means that x is 0, y is 2. Then my y would be 2, which is greater than 1. So that would check. I would shade the region here. Which in this case is going to be the above region. In the event, another thing that could have happened here is I could have picked something that I know is down here, like the origin, which is probably a nice point to pick, 0, 0. So you could say if we picked 0, 0, that would mean your x is 0 and your y is 0. So that would mean that your y is equal to 0. And is that greater than 1? The answer is no, it's not greater than 1. So you would shade the opposite region. Which means you don't want to shade the part where this point is located, you want to shade the other side. So we have a couple ways here. You can either choose to shade above or below, to the left or the right, based on the variable that you're solving for. Or if you're not sure for any reason, just pick a point that you know for sure is in a certain particular region, and then plug that point into the inequality and see, does it make sense? Is this true or not? If it's true, shade the region that includes that point. If it's not true, shade the other region. Questions on that? Let's do the other. Or maybe you guys can just start going through and doing them, and I'll try to catch up to you. sketch pictures of these really quickly. What does x equal 5 look like? Vertical line passing through what?
5.
Well, 5 on the x-axis. Okay. It can be equal to, which means I'm going to draw a solid line. Okay, which region is my solution here? To the left, because my x is less than, your x is less than 5 on the left side of this. So every point in this region is going to be the solution. How do you sketch this? X and y intercept. So to find the x-intercept, you plug in y equals 0. Plug in y equals 0, solve for x. I would divide by 2, I would get x equals 3. To find the x-intercept, to find the y-intercept, plug in x equals 0, solve for y, you would get 6 divided by minus 3. That would give you minus 2. So now you have 2 points on this line. You can be equal to it. Now you just need to connect those points. What region has our solution? Below. A couple ways you could see that. You could solve for the y and realize that you have the y's less than stuff, which makes it below. Another way, pick the origin. That's a pretty easy point. If I plug in 0 and 0 here, 0 is not greater than 6, so that point cannot be in the solution. The solution must be below. So this half of the plane will solve that inequality. This one, same idea. Plug in x equals 0, you get y equals 2. Plug in y equals 0, you get x equals 2. That gives you these 2 points that are on the line. It is less than, strictly speaking, so technically it should be a broken line here. And should it be above or below? The origin would make this actually true, right? So the origin would include the point. So below here would be the solution. All points on that side of the line, not including the line itself, would be the solution. This you can recognize as the line y equals x, so you know that this will go straight through the origin at a 45-degree angle. Or if you, yeah, that's going to be a good nice one. If you did the x and y intercept, you would get the origin being both of them. So what you can do is just plug in some other random point. Realize that if I plug in x equals 2, I'd also have y equals 2. So it'll be on that, and then I can connect those. Either way, you would eventually get there. So now what we can do, since this includes origin, the origin, I pick another random point. Let's say I pick this, 0, 2. So if I plug in x equals 0 and y equals 2, is that true? I'll have minus 2 greater than 0. That's not true. So it will be down here. Another way you can see that is if I were to solve for the y, I would have y is less than something, which means I solve below. If I solve for the x, I would have x is greater than something, which means I shade to the right, not to the left. That was our solution. A few minutes, but we'll pick up from there next time. I see you guys Tuesday. I'll also post some homework this weekend due for next weekend. So,